The next part of the functional analysis here has to deal with the concavity of functions. All right. So graphically, we have here a concave up and a concave down graph. And the reason we consider these concave up, and we'll look at this in definition, if you think about what the slope is here at this point, think of a tangent line, right, coming through here. And if I move to this point, what the tangent line is, if I move to this point, the tangent line, and this point, the tangent line. Okay, so we move across, right? Here we have some negative slope, and then here a little less negative, maybe right here. At that point, we'd have a slope of 0. Okay, as I move this way, now I have a positive slope. I move over here, more positive. So what's happening here is when we have a concave up function, the slopes are increasing. Okay, the slopes of the graph are increasing as we move left to right. All right, likewise here, at this point, the slope of the tangent line, or at this point, here the slopes are getting smaller as we move left to right. So that's a concave down graph or function. Okay. So if we keep that in mind, and now look at the definition of what we mean by a function that's concave up or down. At this point, you could pause it, right? You want to copy some stuff down. But basically what we have here is that a function that's considered to be concave up, right? The definition of concavity, concave up in particular, is that f prime, the derivative, is increasing, right? And the function's concave down if the derivative is decreasing. Now, in order to determine where f prime is increasing or decreasing, it's the same thing we did with f. You know, here when we start with function f, right? If I want to know where function f is increasing, right? Here's some function f, right? How do we know where this function is increasing or decreasing, right? What do we do? Well, in order to find where this function is increasing or decreasing, we want to do what? Find the derivative, find the critical number. So where's the derivative equal to 0 or undefined? And then do little test intervals, right? Set up our little number line, little test intervals to then determine the sign of f prime, because wherever f prime is positive, which again, f prime is just the derivative of f, all right? That means this function f would be increasing. Wherever the derivative f prime is negative, this function f is decreasing. So now, right, if we think about concavity, f prime is increasing. So how would we know where this function f prime is increasing or decreasing, right? We would do the same thing, because how do you know where any function, it doesn't matter if we call it f or f prime, any function is increasing or decreasing where the derivative of that function is positive or negative. So now to find out where this function f prime is increasing or decreasing, we would want to know the critical numbers, which would be labeled in this case as f double prime, right? Is 0 or undefined. And then we would set up a little number line, and now we'd determine the sign of f double prime. And if you think, where's f double prime positive? If f double prime's positive, then that means this function f prime is increasing. But if f prime is increasing, then that means function f is concave up, okay? So it's really going to be doing the same thing we just did with determining where f is increasing or decreasing. It's just that really what we're doing is determining where f prime is increasing or decreasing, which then in turn tells me where this function is concave up or concave down. In other words, the slopes on the graph are getting bigger or smaller, okay? So like I said, you could pause this, right, and read through this. Okay, really concentrate down here. This is like the definition of what we want to do for when we're finding where a function f is concave up or down, and the justifications, okay? So give that a pause. I'm going to jump over to the next screen. So here, determine intervals where f is concave up, concave down, and any inflection points, okay? And we'll get to the inflection points. I'll put some notes in there what inflection points are. So here, we want to find where this function's concave up or down, which means I need to know where f prime's increasing or decreasing. So we're going to need f prime, which is 3x squared minus 6x. So think of this as like a starting point. So if I know where this function's increasing or decreasing, then I'll know where this function's concave up or down. So how would we find where this function is increasing or decreasing? Well, I'd need to find the critical numbers of this function, which means I need to find the derivative of this function, which would be, in this case, notation-wise, f double prime. Yeah, this is the second derivative of f, but really it's just the first derivative of f prime, which is then 6x minus 6. I would then say f double prime of x equal to 0, right? Which would mean that x equals 1. So this is my critical number, right? These are my critical numbers of f prime. All right, now we set up a test interval. In this case, we're going from negative infinity to infinity. Here's 1, and we pick any value over here, okay? Pick 0. You plug now. We're determined f double. We got to plug in f double prime because I want to know where f prime is increasing, which means what is the slope of f prime? The slope of f prime is the value of f double prime. So I plug in 0, I get f double prime between here is negative. If I plug in anything over here, f double prime is going to be positive. So now what does this tell me? Right here, I'm going to write it out. Concave up, concave down is that since f double prime of x is less than 0 on negative infinity to 1, what does that mean? F prime of x is increasing, right? Oh, sorry, is decreasing. Right? So f double prime being negative means f prime is decreasing, but what does f prime decreasing imply about f? F prime is decreasing, and therefore, that's the little quick way, right? Therefore, right? F of x is concave down. Okay. Likewise, since f double prime of x is greater than 0 on, in this case, 1 to infinity, f prime of x is increasing, and therefore f of x is concave up. Okay, so that takes care of the concavity part. Right, f double prime being negative, right, is how you know function f is concave down. And it really tells you, why do you know it's concave down? Because of this part in here, okay? F double prime's negative means f prime's decreasing, which then implies f of x is concave down, because that's the definition of concave down, concavity, if your derivative is increasing or decreasing. Now the point of inflection stuff. What's a point of inflection? Okay, so we're going to say let c f of c be defined. All right, so you can't have a point of inflection at a place where your function's not defined, so we're going to start with that. And then we're going to simply say if the concavity changes at cf of c, all right, then cf of c is a point of inflection. Okay, so that's what a point of inflection. It's a point of inflection is where your concavity changes. All right. Now, how are you gonna know concavity changes? Well, concavity changes because f double prime is going to change sign, right? If you have a change in sign at f double prime at cf of c, that means your concavity changed. All right. Now let's think also something else a point of inflection is, right? Graphically, let's look at a graph. Wrong key. Right? Here's concave up. Then right here at this point, let's turn to concave down. Right? So right here, that would be graphically a point of inflection. Okay? I went from concave up to concave down, right? Over here, what do we have? Over here, f double prime is positive. Over here, f double prime is negative. So that's a point of inflection. Now, keep this in mind in terms of what else does it mean? Well, if f double prime is positive, yes, this means this is function f. It means f is concave up. But what's it mean about f prime in here? It means f prime must be getting bigger. My slopes are getting bigger. Then over here, my slope f prime is getting smaller. So you think f double prime being positive means f prime is increasing. And then at this point, since f double prime is less than 0, f prime is decreasing. So what must be there for f prime? That's a relative max. Okay. So another thing a point of inflection is, points of inflection are also relative extrema for f prime. Okay, it's a localized steepness, a max steepness, right? What's the slope here, the tangent line? Like 0. What's this? I don't know, maybe it's 1. As you approach here, right, coming through here, and then as I move away, notice my tangent line over here is smaller, over here is smaller. Right there, it's a kind of a max or min steepness. Okay, localized. All right, so that's your points of inflection. So then we go up here, we answer the last part for this example. Do we have a point of inflection here? Yeah, because here f double prime is negative. Here's my sign chart. It's easy to look at a sign chart. F double prime negative, f double prime positive. So at 1 and at x coordinate 1, there must be a point of inflection. As long as 1 is in the domain of f, which it is. The domain of f here is all real numbers. So here, that means we have a point of inflection. All right. Right, of what? 1 comma. Now, where does this go? It's a point of inflection on function f. So that means you got to plug 1 into function f, not into f prime or not in f double prime. Plugging in here, you get 1 minus 3, negative 2 plus 3, 1. All right. So 1, 1's a point of inflection. And why do you know it's a point of inflection? 1, 1 is a point of inflection since f double prime changed from negative to positive, right? Means your concavity changed. You could say that as well, since f changed from concave down to concave up. All right, both those would be fine. All right, so there's that one. Let's go over here. We have this function, so let's do the same thing. Okay, find my concavity, concave up, concave down, and then any points of inflection. So here, another thing here, just keep in mind domain, all real numbers. So that means anytime I see sign change, whether it's for f prime, maxes and mins for f, or f double prime changes in sign, which would be maxes and mins for f prime, which would be points of inflection for f. All right, I know that they're going to be points of inflection because they're in the domain of f. So we're going to need the derivative, 24x squared minus 8x cubed. We're going to need the second derivative, 48x minus 24x squared. We need to find critical numbers of f prime, so f double prime. F double prime of x equals 0. Now, if we look at this and set this equals 0, we're going to factor out a 24x. That would leave me with 2x. Leave me with 2 minus x equals 0. So I get x equals 0 and 2. Now I set up a little quick number line. We got negative infinity here, 0 here, 2 here, infinity over here. Keep in mind, we're looking at f double prime. So in here, what is f double prime? Okay, here's f double prime. I could plug in here, but also the better, a better place to determine sign is right here. That's a better place to look. Okay, so if we think here, 24 times x, well, if x is negative, that's a negative. So anywhere over here, I already know that's negative. And then 2 minus the negative is positive. So you just go, oh, well, that's a negative times a positive is negative. So negative in here. I don't even need to plug in a value. Just know that I'm negative over there. In here, 1. So 2 minus 1, 24 times 1, positive. And you think anything over here, 10, positive, negative. There we have it. All right. And now we'll formalize everything. Okay. So we know where function f is concave down. So we say f is concave down on the intervals -infinity to 0 and 2 to infinity, since f double prime of x is less than 0. And then we write f is concave up on 0 to 2, since f double prime of x is greater than 0. So there's formalizing our concavity with justification. That's all you need to write. And then do we have any points of inflection? We go from negative to positive, f double prime does, and we go from positive to negative. There's a sign change. 0 is defined in f, 2 is defined in f. So we have points of inflection. So then we say f has points of inflection Now, sometimes it might be what is the actual point of inflection or just the x coordinates of the points of inflection. So if it's just the x coordinates, then it's just at 0, at x equals 0 and x equals 2. If it's the actual, what are the actual points of inflection? Has points of inflection of 0 and then plug into f, 2, plug into function f. Up here, if we plug in 0, we get 3. Plug in 0. And then if we plug in 2 here, we get 64. Minus 32 is 32 plus, we get 35. So there's your points of inflection. And then we could justify it since f double prime changes from what? We went from negative to positive and positive to negative. Done. Okay. So that's all there is to that for your concavity. All right. Another little note to make here. Make a note of this. Critical numbers are possible extrema. They're candidates for where extreme values, maxes, and min can occur. So critical numbers are possible extrema. All right. Now, conversely, if there is an extreme value at x equals c, then x equals c is a critical number. Okay, so just make note of that just because f prime of 2 is 0, it doesn't mean that there's a max or min at x equals 2. Okay, if f prime of 3 is undefined, doesn't mean there's a max or min at x equals 3. There might be, there might not be. However, if I'm telling you that there's a max at x equals 2, then you know that f prime of 2 or f prime of 2 is 0 or undefined. Okay, so it's a one-way street in terms of what you know. It's kind of like the differentiability implies continuity for sure, but continuity does not definitely imply that the function is differentiable. Okay, and then the other thing here, it's called the second derivative test. So this is used for maxes and mins. So this is called the second derivative test for extreme values. All right, and you can see here that what's going on is that if f prime of c is equal to 0, so we have some function where f prime of c is equal to 0, the second derivative exists around x equals c. Okay, so that's what is meant by, in an open interval containing c. So in the area, in the region of x equals c, the second derivative is defined. And what happens here is that if f double prime of c is positive, that means the function's concave up. So if you think if the function's concave up, then that f prime of c where it's equal to 0, the slope of 0 is going to be that low point of the valley, say, right? So here f double prime means you're concave up. And if f prime of c is equal to 0, that means this point right here, right there would be f prime. It's going to be a min. Okay. If f double prime of, oh, sorry, I didn't reverse. Yeah, concave up. Right, I was thinking this one. F double prime of c is positive, right? Concave up. I said negative, but concave up. And here then we have a minimum. Here, if f double prime of c is less than 0, right, that would mean we're concave down in an area where f prime of c is 0, which would mean it would have to be that point. So clearly we could see that there's a max. And then if f double prime of c is not is equal to 0, then this kind of breaks down and you just have to go back to the first derivative test, which is my function f increasing to the left and decreasing to the right, or decreasing then increasing, which would tell you max or min. So here, let's do the second derivative test, right, and see how this works. So in order to do that, we want to find where's their max and mins. Well, possible maxes and mins occur at critical numbers, right, of f. So f prime of x equals 30x to the fourth minus 30x to the fifth. We set this equal to 0. Here, f prime of x is equal to 0. Factor out here a 30x to the fourth. Right? And then multiply by, well, what's left? 1 minus x equals 0, in which case that tells me that x equals 0 or 1. Right? And now, what about f double prime? All right? If I look at f double prime of x, that would be 120 x to the third minus 150 x to the fourth. And now this is where, well, let's see, f double prime of 0. Now here's a, right? That's a possible candidate, right? F prime is 0 at 0. So f double prime 0 is equal to 0. So in this case, the second derivative test doesn't tell me if there's a maximum in there. I have to go back to the first derivative test. So we'll do that in a sec. And then f double prime of 1 in this case is equal to what? F double prime of 1 is, well, here, plug in here 120 times 1 minus 150 times 1 is, right, negative 30, which is less than 0, which means that if f double prime is negative, we must be concave down. So that means we must have a what there? There's my derivative being 0, f prime being 0, in this case at x equals 1. So this tells me right away that there's a min at x equals 1, since what? F prime of 1 is equal to 0, and f double prime of 1 is less than 0. So that would be the justification for why you know there's a min there. Now, if we go ahead and check the this one at x equals 0, we can go back up to the first derivative, which is right here. Quick little number line. Here is 0, so we check over here, negative. This is always positive, right? 1 minus a negative is positive. Positive times a positive is positive. And if I plug in a value over here, say 2, I got a positive. 1 minus 2 is negative. So I get a negative. So you can see here that we went from positive to negative. F prime did, which means f went from increasing to decreasing. So now the first derivative test tells me there's a max at x equals 0, right? Since what? F prime changed from positive to negative. Okay, so that would be going back to the first derivative test. Okay, so that's what the second derivative test is. And nothing, for here, I think what I'm going to do is leave these. If you want some extra practice with these, or try these out, right, with those functions. The trig ones, keep in mind, product sine times cosine, right, doing that one. But for a little bit of sake of time of the length of the videos and stuff, we could leave that for another practice exercise for you if you want to do that and check in the answers. And these are non-calculator problems. But at the end, you could always just graph them and check, right? See if the max or min that you think you have, You have. The big thing that you should practice here a little bit and understand is how to formalize and write your answers, right? Why the justification. Going back over to here on a free response, you have to write out, show your work. So I showed my derivatives. I showed how I know the critical numbers, that the second derivative is equal to 0. I don't necessarily have to show the algebra to get it, just right. I use this to get my information. Then right here, this last all this stuff here, right there. Let's put this would be all the formalization of your answer and justifications. Okay, so that's what you really want to pay attention to as well. So watch this over. Reach out to me if you need any help. You want me to explain anything further. Okay, and we'll get going from there.